with Mike Yagley from Cobra Golf, and as you can see, we have a mock-up of the F7 driver here, and there's a lot of different parts, a lot of different materials that go into making a driver head what it is, essentially how it's going to perform, how it's going to sound. And, as somebody who designs these driver heads, I kind of wanted to ask you about the different materials and what exactly does go into making this driver something that's going to perform for a guy like me.
So I'm going to go back about 15, 20 years, and I was working for Boeing, designing airplanes. And I was working in a group that was literally tasked with designing high-speed civil transport. So we were, and this was like next generation Concorde. And the group had a propulsion system group. We had an aerodynamic group, which is I was in. I was in the low-speed aerodynamic group, structures group. You had a fuel system group. You had a payloads group. You had all these groups.
Okay.
And it was a very complicated structure and a very complicated problem that we didn't even know if we could converge on a solution, right? To make a supersonic transport that could actually be cost-effective, met the sound criteria for takeoff and landing, was able to transport the number of people you want to transport back and forth. Okay, highly complex problem. I get into golf and I'm thinking, oh, this is going to be easy. Right?
Smaller scale.
Yeah, it's small. It's how big a deal is this going to be? Shocking at how complex and how difficult it is to make this simple-looking little structure sound good, feel good, perform well, and be durable. There are so many things going on inside a golf club that I was shocked. And when I described it to my aerospace buddies and my former Boeing buddies, they had no idea. And a lot of them are golfers, right? You look at it, it's a golf club. How hard can it be, right?
Yeah, it's pear-shaped. I swing it. I hit the ball. Simple.
So I'm here to tell you, this is a highly complex structure that has to do things that rocket ships and airplanes aren't required to do. And like I said, look good, feel good, sound good, and perform well. So let's start with the face, right? Simple titanium plate, right?
Okay.
Now we've gone a little bit exotic. We're using 811 tie, which is a lower density, high strength, very resilient titanium material. Okay, seems simple enough. Well, check out the back, right? Do you see the contouring that's on there?
Yes.
Right?
Right in there.
Yeah, so imagine man months or more optimizing exactly where these pads are. Well, this is thin, that's thin, and that's a little bit thicker, and you can see that shape.
Yep.
Right? I changed that shape by literally fractions of a millimeter, and you go from a golf club that sounds good, feel good, it's durable, right? And then suddenly we find out in FEA analysis that it starts cracking, right? We find out that it's either too fast or too slow from a resilience standpoint. We find out that it actually starts to sound poor just by changing the face thickness by fractions of a millimeter. Okay, that's just the beginning. You get into then the entire head, and again, you look on the outside and you're like, oh, that's a fairly complex structure, but look what's going on the inside, right? In order to put a 12 gram weight in any of these locations and have it survive, have it sound good, look at the rib structures that have to be added in order to make that work. And these ribs, you can see the length and the thickness of it. You change that thickness by, again, fractions of a millimeter, and you go from a weight that is held on here very nicely and it survives thousands of hits to, nope, it rips right out, literally in just a couple of hits. Or you go from, say, 3,800 hertz, which is a really good sounding golf club when you've got the weight in that position, and you move the weight over to this position, you change these ribs just a tiny bit, and it goes to about 3,200 hertz, and you and I would both say that is the worst sounding golf club we've ever heard in our lives, right? On the same head. So our designer and research guy in my group spend an awful lot of time optimizing these, what seem like little simple rib structures, the location, the thickness, the height, so that when you put the weights in any of the positions, it sounds basically the same, feels basically the same, so that you don't have any complaints. Right? These are all the things that we've got to really grind on hard in the background. And we just started here with the tie structure. You move into the hosel area, and you can see, unlike many of our competitors, there's no structure in between the hosel and the base where the screw sits. There's nothing in there. See that?
Mm-hmm.
That saved us several grams of weight. So we had to engineer the heck out of this thing so that we could remove that weight and put it in places where we really wanted it. And again, it would survive 3,000 hits. It would still feel good. It would still sound good. You look at the rest of the head, and we put a carbon fiber crown on here, and you can see a texturing pattern on there. This crown, if it were made out of titanium, would weigh several grams more, which would raise the center of gravity, which would lower the moment of inertia. So we work really hard at putting an extremely lightweight crown on top of this head. And the structure required to bond it, to get it to stay on, feel good, give you the sound properties that you want, give you that 3,800 hertz that we're talking about, incredibly hard to do. From a shaping, from a thickness, from a overall, like I said, attachment to that head standpoint, getting it to stay on, not crack, not a trivial exercise.
So it's not rocket science, but it's more difficult than rocket science, essentially.
Honestly, it's a heck of a lot more difficult than some of the things we've had to do, that I've had to do in my career, to make a rocket fly, to make an airplane fly. Yeah, it's a very, very complex, highly dependent on mass property, structure, how it's bonded and joined, right? And optimizing the feel, the sound, the durability, the overall mass properties. Very complex problem.
One last question, talking about weight savings. So we talked about how there's nothing here which saves weight. The lighter crown saves weight. Smoothing out some areas of the face saves a little weight. When it comes to reassigning where that weight goes, if you're going to, or you can just completely remove it, but how difficult does it become to figure out if the weight's got to go on this rib structure or anywhere else within the head, so that it doesn't adversely affect all of those other things that we've been talking about?
I would express a difficulty in time. So the short answer is it can be very difficult. And we could literally move one of these weight ports just a couple millimeters, and it could take weeks for the guys to go back and forth to figure out exactly what the rib structure needs to be, what the thickness of the titanium in that area needs to be in order to hold that weight properly and sound good. So it's one of my favorite phrases it's not trivial.